Okay, so we're going to look at Newton 1 a little bit more closely. So this law is just basically a brilliant piece of deduction. So Isaac spotted something which was pretty clever, but actually really simple. And he said a body will continue in its state of rest unless an external force is applied to it. So let's take an example here. So what do we mean? So let's take a ladder. So you might use a ladder. So take, for example, a simple uniform ladder with its foot. We've got some sort of roughness here. This is a wall, and then this is some sort of roughness on the bottom. Uniform ladder. And it's against a smooth wall, so all the force is actually acting here. There's no force affecting there. Where the mass of the ladder is uniformly distributed, so its weight, as we found out last week, uh, is going to be somewhere in the center. When we looked at our center of gravity last week. So what do we actually know? Well, there are normal. Well, we'll see what the rest of the question says. Here we can see the ladder is equilibrium, and the weight of the ladder is spread over the 2 points. So here we're going to actually have two forces. We've got a resistive a resistive force here, and we've also got a force here as well. So our ladder is in equilibrium because of these two forces. The force here, which is stopping it from moving, which is balancing out our W, and our resultant force here, which is balancing out our W component. But what does that actually mean? So if you were to think of this as different points, is well, we have this ladder here like this, which is at some sort of angle. And what's stopping it from floating away? Well, the weight of it's stopping it from floating away. But as I've said, that we've also got this reactive force here. So the force which is keeping it on the ground, which is keeping it level, well, that would have to be here, and that would be the same component as W. But also, we'll have a force here, which is stopping it from moving away from the wall. So that force is equal to the opposite of that. So that would be the component of W, which we would just bring round here. So we can work that out with some basic trigonometry. So let's maybe look at an example of this. So maybe we have a inclined plane. This is maybe more of a classical example. And on this inclined plane, again, it's got a wall here. This is all solid. We've got a single ball. And then, so what do we have with a single ball? Let's think. So the first thing we would have is this ball has got a weight. So keeping it in place, it says that this inclined plane is rough. So that means that there's a force acting this way to stop the ball moving downwards, right? And likewise, we have the weight pulling it down, but also if the weight's pulling it down, well, there has to be an equal force, which is its normal force, which is reacting against it. Otherwise, it'll be floating off in the air. So it would be pulling down to the ground. So we have to keep it in equilibrium. This is what Newton 1 was saying to us. So how could we calculate these different forces, and what can we actually calculate these components? So as I said, this is a frictional force and this is our weight. So what we can do is we can work out just one force or one vector which is pulling this down. Maybe we can think of this just about the plane. So if we think what's going down the plane and what's going up, okay? So we've been told that this is at 30 degrees. So if we were to draw a table that looks a little bit like this, and first of all, we were going to see the forces which are going down the hill. So, well, we've got actually our frictional force, which is going the opposite way. So that's our frictional force, which is minus F. And reactional force, well, we don't have anything else because we're going only up and down the plane. So that would be 0. And our weight, what's our weight? So we want to find out what weight is pulling this down. So here we have to do a little bit of trigonometry again. So what we want to do is we want to resolve this W so as if it was to pulling down the hill. So what we can do here is, well, we can see that we have, again, a right angled triangle. So what this would then equal is W sine 30. So if you don't understand where I've got that from, you just need to go back and do a little bit of trigonometry, and you can see that that would work out as this W comes round acting this force, because of this angle is here, we also have the same angle here because of the Z angles, and that means that we have this W sine 30. Likewise, we can see the frictional force if we're going upwards. Well, there's no frictional force. We're not taking it into consideration. No air resistance. It's very fine. Well, what have we got here? The reactional force. Well, the thing that's stopping it from accelerating down into the ground, it would be N. And then our opposite force, well, we have here our force coming down. So again, this is our 30 degrees here. So that would make it W. This is a closing angle, which will make it cos 30. And this is a negative force as it's going downwards. So that would be, it's the opposite of N, which would be W cos 30. So all I've done here is, as you can see, negative, I didn't point out, the negative points correspond to the arrows. So the weight is pulling it down, so that's positive, and the frictional force is upwards, so that's negative. This could be the other way around, it doesn't really matter. So our reactional force is N because it's going upwards, and our weight force is negative because it's going downwards. Again, these could be either way around, it doesn't really matter. So what does this give us? Well, actually, we could resolve all these. We could add them all up and see what all the forces are going down. So if we were to add these up, the force going down, we would find is equal to W sine 30 degrees minus F. And the force going that way is equal to our reactive force. We have R, which is N, which is N minus W cos 30. Okay, so if we wanted to now calculate the resultants of these, well, this would be quite simple because we just have a triangle. Our triangle looks a little bit like this. Okay, so where we have our two components, which we've worked in both directions, where if we wanted to calculate the resultant force here, and our angle, we just use the same process as what we did earlier. So our normal force going up here is N minus W cos 30. And here we have W sine 30 minus F. Therefore, if we wanted to find out the resultant, all we need to do is we just need to find what R would equal. R is equal to W sine 30 minus F squared plus N minus W cos 30 squared, and we'd find the square root. And likewise, all we'd need to do to find the difference between the tan angle is we would just need to find our triangle again, which is here, and we just need to use our tan degrees, and we can find from this that we have our triangle. If we were to just draw this out and draw it out like this, and we have our N minus W cos 30, and here we have our W sine 30 minus F. So this is just this point, and this is just this point. So if we wanted to calculate this, we have our opposite and we have our adjacent. So this would be N minus W cos 30, all divided by W sine 30 minus F. And then this would just give us our angle if we were to solve for theta. So effectively, what we've managed to do here is we can simplify this point. And what's this basically telling us is that if we have we have on our slope like this, we have a ball sat here. Well, the force, which is the sum of, well, the reactive force, the weight, which is stopping it from forcing going all the way down, and the force which is stopping here, is actually equal to a force which maybe it's about this direction, which is stopping it from floating away. So we have this single force which is describing both the frictional forces, the reactive forces, and the weight forces as well. Okay, so I'll give you another example here, maybe a little bit more difficult. So perhaps it says we have a uniform ladder, and there's a picture here as well, a uniform ladder. Let me make that line a bit bigger, something like this. The uniform ladder is placed against a wall that looks a little bit like this, and we have, this is at 10 degrees. So the question states, a uniform ladder of weight W rests with its top against a rough wall and foot on the ground with slopes of the base of the wall at 10 degrees. Resolve horizontally and vertically and calculate the forces on the acting on the ladder. So that means we have a reactive force here because it's pushing, and also we said that we have a resistive force on the wall, so that would be F1. And then on the bottom, we also have to have something stopping this moving because this is going to be a rough bottom as well. So that means we'd have a force which is here, which is F2. And of course, we're going to have a reacting force here. Okay, so we're going to call that R2. So what we want to do now is we want to resolve these forces. But unlike in the previous case where we had this nice kind of perpendicular lines, we don't actually have this. So we can choose one of two ways. We can choose the difficult way or the easy way, and I'm going to do the easy way. So we can resolve all our forces either vertically and horizontally because we know this 10 degrees. This might be a little bit more difficult. Well, it would be very similar to actually do this to these forces here, but we'll keep it simple. Okay, so all of our forces going vertically. So what have we got? We have F1 and our next one, so we have a F2. But okay, so we want to work out what that is horizontally. So we have a little triangle here. So if we were to calculate this, we have F2, and that would be our cosine. So we'd have minus, because it's going in the opposite direction. Sorry, we want to work on our positive, aren't we? Sorry, I read the wrong one. We want to be the sine of the angle if we're going in this direction. So if this is what we've been given here, our sine 10 would give us our positive, which would be positive F2, and that would be sine 10. If you've not followed this, just go through and work out the trigonometry. And we also have the weight, which is coming down, so we want to negative the weight. And what else are the forces we have? We have this R force, so this is also at 10 degrees. So 10 degrees here would make that a cos, so that will be plus R2 cos 10, okay? And our horizontal forces, I think this is opposite in the way that's in the book. We have our R1, which is just here. We will also have do we have a weight force? No, we don't have a weight force because it's always going down. We're just solving that way. Our second force, which is our F2, well, that has a horizontal component, so that's closing, so that'll be F2 cos 10. That's our little angle here. And then we have our R2, which again would be a sine angle now, so that would be R2 sine 10 degrees. Okay, so if you've not fully followed this, as I say, go back, work through the trigonometry. It's just straightforward trigonometry. It just takes a little bit of drawing the triangles out. So what we have here now, we have two forces resolved, which if we wanted to, we could then say we could calculate between the two. We have the positive, we have this one, the up, and we have the vertical, sorry, and the horizontal. So therefore, we could calculate the resultant force of the two, and we could even calculate theta here as well. So we could see the single force which is stopping this ladder from floating in the air. Okay, so a final example here is kind of more of an exam style question. So the question states, calculate the resultant of the forces 4, 6, and 2 and 3 newtons shown in the diagram. So let's just draw the diagram out. So the diagram looks a little bit like this, a little bit like this, a little bit like this, a little bit like this. Oops, I've got to go the best. A bit like this, a little bit like this. And this isn't to scale by any means. 6 newtons, 2 newtons, 4 newtons, and 3 newtons. We're also given some more information. There's a dotted line here, and we can see that we have 60 degrees to the normal, and we have 60 degrees. Okay, so it's even. So what this is stating, we have all these forces acting, and at this point is staying constant in the middle. This could be a particle or a ball. So first thing we want to do is find the vertical and the horizontal. So let's try the horizontal first. So what have we got as horizontal angles? So first of all, quite simply, we have this 4 newtons. Okay, so next we have our 6 Newton component. So this component, so that would be plus R, so this direction is the same direction as 4, which would be 6 cos 60. And then in the other direction, we have 2 newtons. So it's going in the other direction, so it'll be negative 2 cos 60 again. It's the cosine. And then in the vertical, we have 3 newtons. So this is going down. Maybe we'll keep down as our way of writing this, newtons. And then what do we have here? Well, we have 60. This is actually going to be a vertical. These are 90-degree lines. So we could say that would be plus 6 sine 60 plus 2 sine 60. Okay. And if we were to add all these up, we would see that in our horizontal, we stick these into the calculator, we would get that that would be equal to 6. And in our vertical, that would equal 3.928 newtons. So don't forget the units as units here. So therefore, we've simplified this into just these 2 components of vertical and horizontal. So what we want to do now is we want to see if we can find a resultant force for this. So if we just think of these, we have this horizontal and this vertical, we draw a triangle. We can say that we have our 3.928 here, and we have our 6 newtons here. And we want to find the force which is in the middle, which we've said before is equal to R equals 3.928 squared plus 6 squared, square root it all, and we find our R is equal to 7.17 newtons, which is great. And if we wanted to find out our angle theta to the horizontal, all we would need to say that that would be the same as saying tan theta is equal to our opposite over our adjacent, which is 3.928 divided by 6. So theta would equal 33 degrees. Okay, so that's just how we resolve some forces. So all this is trigonometry. You've done it before. It's just thinking about it in a slightly different way. Next, we're going to move on to something a little bit more tricky. We're going to look at Newton 2.